what is the most mechanically efficient and chemically precise way to control our breathing, in my opinion, we best left that to the brainstem. And I think within a dozen breaths, all of a sudden I could feel my legs just so much stronger. I couldn't believe it. Well, if you have a higher demand for oxygen transport, but a major organ that delivers oxygen has not adapted, will it get to the point of failing as a gas exchange? And I think that's what we can really teach our mentees, to seek out criticism, to seek out feedback, to seek out the best people you can about your science. You can't go wrong.
Welcome to the Upside Strength Podcast, the fitness and performance resource in Switzerland. Today, I have the great honor to welcome on the show Dr. Jerome Dempsey. Jerome grew up in Canada and is a Ph.D. in applied physiology from the University of Wisconsin and Professor Emeritus since 2008. Welcome to the show, sir.
Thank you. Great to be with you.
It's a pleasure to have you on. So to get us started today, could you talk to us about how you first got interested in the sciences and then more specifically the respiratory system?
Yeah, when I was an undergraduate at my university in Canada, London, Ontario, I did well in the sciences class, but I didn't have a particular curiosity for them. But I had a professor there, a guy named Michael Uhas, who just died a year or so ago, who was a fitness guru. And I don't know what he call what he did was science, but he was just infatuated by fitness. So this is late 1950s, and fitness was not a big deal back then, but to this guy it was. And he even started corporate fitness. He was an author of one of the authors on a thing called the 5BX plan that the Canadian Air Force put out. So he needed student help with running classes like this. And that's who really got me started in being curious about what made the body work and how exercise affected it, etc.
And then how about the respiratory system? How did you get into that?
Well, when I was a high school teacher for a while, then I went back to school because the curiosity came up again at the University of Alberta. And I met a man there by the name of Brian Spool, who was a respiratory physician. Really brilliant, bright guy who had done exercise with Jerry Mitchell, a very famous exercise physiologist, physician in Texas. That's who really got me interested in the respiratory system. Then at the University of Wisconsin, my mentor was a Scot by the name of John Rankin. And that absolutely solidified it. Because I went down there to study fat cells, which I did for several months. But I found that very interesting. It was on causes and consequences of obesity. I thought it was an interesting field, but the lung was so much more interesting and complex and fascinating. So Dr. Rankin and Dr. Spool were the two that really turned me on to this.
Do you remember a specific fact that attracted your attention about the lung and the respiratory system?
Yeah, I think the first couple of projects that I got involved with was how exercise affected the diffusion capacity of the lung. And I saw just with the minimum amount of exercise, we were measuring diffusion of how quickly the lung adapted and how near perfectly it did. So while muscles were producing lactic acid, while there was inadequate stroke volume, the lung was this gorgeous, near perfect response. And I was fascinated by an organ that would be that perfectly suited for exercise. And I guess that's what got my enthusiasm going even more. And then we actually, back in the 60s, we did a few sleep studies. And when you can see the system that controls our breathing in the brain and reflex system that are just on automatic pilot during sleep when you take out the higher nervous system from it, and how beautifully that operated. That was another example that I became very curious about that. So those are a couple of areas. And then the third was, again, back 50 years ago, we went to high altitude. There I saw that, well, things weren't quite as perfect as they were at sea level under those previous two states that were, while the respiratory system was adapting, it seemed, quite nicely to high altitude. Mm-hmm. People were short of breath. The work of breathing was high. The vessels in the lung were constricting, not dilating. All of a sudden I thought, whoa, this system is not perfect. And there are conditions, very foreign conditions like hypoxia, that can really challenge it. So, I mean, as a scientist and a physiologist, how could you look for anything better than something that was as diverse, complex, and perfect and imperfect all at the same time to study? So that's what got me going.
Like that, to get us started, I want to talk about maybe something that's paradoxical about breathing is like you said, it's the autonomic control or lack of control that is essentially the autonomic drive to breathe. So if we don't think about it, we breathe. If we sleep, we breathe. If we're unconscious, we most of the time keep breathing as well. But at the same time, if we decide to change our breathing, we can. So can you talk a little bit about that paradox?
Yeah. And there are different neural pathways for that too. If the cortical spinal pathway bypasses, at least in some of its pathways, will bypass the medulla, which is the major autonomic site, mm-hmm. or automatic site for controlling breathing. But you can voluntarily control, even bypass those sites. So even different neural pathways for that control. And so, yes, that's there. And it's good that we have, because we cough, we phonate, that's all part of the control of breathing. So we need voluntary control for sure over our breathing. But from the point of view of what is the most efficient, mechanically efficient, and chemically precise way to control our breathing, in my opinion, we best left that to the brainstem and let the automatic control dictate that. For example, with an athlete, I know that I've heard coaches talk about this, and I've heard physiologists talk about it, that we should teach runners, for example, to breathe with the foot plant. So that would be a voluntary control in stride. And because it turns out that some do and some don't, just automatic. We should do that. We should have them breathe with their diaphragm. Well, I'm very much against that. You don't have to tell anybody to use their diaphragm to breathe. This is our major, far and away, inspiratory muscle. It's going to be used. And what we know now is that but the diaphragm will fatigue with exercise. If you exercise long enough and hard enough in a healthy person, and you can see fatigue of the diaphragm. You can test that actually by stimulating the phrenic nerves and measuring the pressure developed by the diaphragm. And long-term heavy exercise, before and after stimulate, you'll see about halfway through that, you'll start to see the fatigue develop in the diaphragm. Doesn't mean it can't produce force, but its ability to produce force is compromised. Mm-hmm. So, but that far and away, you're much better off in having the involuntary system dictate which muscles you use, which lung volume you're breathing at. That's absolutely crucial. So that you're breathing on you're using the least force to produce a given flow rate and a given volume. And during exercise in health, if you don't have precise control of breathing frequency and tidal volume, precise control of your expiratory muscles, which starts even in mild exercise, you will not breathe on the most efficient part of your pressure volume relationship, and it'll be an inefficient, and you'll become aware of your breathing, and the energy cost will be too high. That would be my prediction. I've never seen a study carefully measuring breathing mechanics with voluntary versus involuntary control, say in heavy prolonged exercise. Maybe somebody's done that, but I'm not aware of it. Might not be a bad idea to try. My prediction would be leave the cortex out of the control of breathing as much as you can.
Yeah, so the system is smarter than us.
Oh, it's terrific. All the feedback and feedback control of that system, lots of which we don't completely understand the fundamental mechanism. But from all of my observations and those of many others, it seems to be an extremely efficient way to breathe. It's not that you don't have zero energy to breathe. As we sit here at rest, of all the oxygen you consume, of all the cardiac output you put out, about maybe 1% of that's, 1.5% of that's going to the chest wall, to your respiratory muscle. If in an untrained person at their VO2 max, where you're breathing maybe 110, 115 liters a minute, maybe 8 to 10% of that cardiac output and ventilation will go to respiratory muscles. In the highly trained athlete, depending on your age and your sex, as high as 15, 18% will go to the respiratory muscle. So it requires energy, but you want to keep that as low as you can so that the brain, the heart, and the locomotor muscles are sharing as much more of the cardiac output as they can.
So building onto that now, can you talk about the ramifications? One thing I find fascinating about the respiratory system is its impact and relationship with many, many other different systems in the world. You just talked about in the body. Sorry, you talked about the brain. You talked about the heart, the muscles. So can you talk about all the different relationships that the respiratory system has with the rest of the body?
Well, yeah, it's kind of for transporting oxygen, getting rid of CO2. That's kind of first principles. You have to do that. You want to do it the most efficient way you can. Well, one area of research which is still we have a lot to find out about from a integrative physiology point of view is how respiration and circulation coordinate and affect one another. So, for example, when you take a breath, you develop pressures within the chest. And these intrathoracic pressures are surrounding the heart. And that will affect the venous return to the heart. It will also affect the ability of the left ventricle to fill, because you don't want pressure exerted against that. So, for example, in highly trained athlete at very high exercise levels, they produce huge expiratory pressures during, high intrathoracic pressures during inspiration. Part of that's due to the fact that they get to the point where the airways are limited in their ability to produce flow. And so you produce these huge pressures without having more flow, really. They've reached what we call flow limitation. Well, that will have an effect on how much you breathe. It'll limit the breathing, ventilation, which has effects on gas exchange, but it also affects the ability of the ventricle to fill. And this will affect stroke volume. So that's one example. Another example of an interaction between the respiratory and cardiovascular system, are the respiratory muscles. When they start, just like a locomotor muscle, if they work to the point where oxygen transport is not sufficient, they'll start to produce metabolites, lactic acids being a primary. And that muscle becomes acid. Well, it turns out that the phrenic nerve, which is the main motor nerve to the diaphragm, for example, or intercostal nerves to other accessory muscles, that there are as many fibers that go from the muscle to the brain as there are coming the other way, sensory and motor. So what do those sensory fibers do? When the muscle starts to become acid, it will have afferent traffic to the brain, which will affect sympathetic nerve activity, which will affect the distribution of blood flow throughout the body. So that's a couple of ways in which the respiratory system interacts with the cardiovascular system. And of course, it has implications for oxygen transport to muscle and how the skeletal muscle will function as well.
The last one you mentioned, is that what is called the metaboreflex?
Yeah, this is, we've known about metaboreflexes for several decades. The one we usually think of is the one from the, excuse me, from locomotor muscles, say in the limbs. So that it activates the sympathetic nervous system, which is responsible for the rise in blood pressure we have during exercise, and causes, it really prevents the vessels in the limbs from dilating too much. Interesting, isn't it? I mean, you want them to dilate, and they do. I mean, 80% of your cardiac output's going to your locomotor muscles when you exercise. But those vessels have such a huge capacity to dilate. You don't want them to be unchecked. So the sympathetic nervous system is activated to keep a kind of a constriction, a tonic constriction on those muscles to not let them dilate too much. And that, and one of the reflex receptors, which is responsible for that, is a metaboreflex from the locomotor muscles. So all we're saying is that there's also evidence to support metaboreflex from the respiratory muscles. And it will affect the sympathetic nervous system, much in the same way that metaboreflexes from the limbs will.
So to make sure I understand it properly, the metaboreflex from the respiratory system or from the diaphragm, let's say, once it fatigues, what's essentially going to happen is it triggers a signal to the brain that says, hey, let's limit the flow to the locomotor muscles so that we can get a little bit more of that flow so that we can not fatigue too quickly. Is that correct?
That could be their thinking, okay? But it's not, we don't know whether it's their thinking, it's our thinking, because we have to have a reason for everything, right? It's called teleology. Sometimes teleology can really screw you up if you take it too far. It could very well be this just an error in the system. And it's responding to a muscle not getting sufficient oxygen transport and accumulating metabolites. You know, so the other thing that I'm unsure of is that I wonder if this is, and this is not me suggesting this, has been around for a while, if this feedback from a fatiguing diaphragm and respiratory muscle may also be signaling the brain to tell that muscle, slow down. You are a major inspiratory muscle, okay? If you keep working this hard, you're going to fatigue completely. And that's not good when you're, you know, the old idea, you're trying to escape the saber-toothed tiger, okay? So when I used an animal model to look at this, and other people too, I see a big effect of this metaboreflex on sympathetic nerve activity and blood flow distribution. But I haven't seen, at least in vivo in an exercising animal or human, evidence that it has a big effect on the control of breathing. That's kind of disappointing. I thought for sure it would have a negative influence on that, because what we see, I saw this many years ago, almost 30 years ago, that in heavy prolonged exercise, it produces the documented fatigue of the diaphragm. That you start to see that even though the ventilation's rising over time with prolonged heavy exercise, even at a fixed workload, that you start to see the diaphragm being used less and less, and other accessory muscles being used more and more. I saw a review article by a former graduate student of mine, Ralph Fergosi, not long ago on the respiratory muscles. They estimate from EMG evidence that up to 50 muscles are probably used during heavy exercise. 50 so-called respiratory muscles.
For the inspiration and the expiration.
postural muscles, but they're used to produce a breath. I think that's really interesting, and I believe it. Like for example, the sternocleidomastoid muscle, Bill Shield at University of British Columbia has shown recently that this increases in direct proportion, and the blood flow keeps increasing to it, the harder we exercise. And we never use this just sitting here taking a breath, but it's even in mild exercise starts to become incorporated as a primary mover to lift the rib cage.
Which would explain that increase in blood flow and O2 consumption at higher intensities, going from that kind of 1 to 10 and 2 or 3 to 15 or 18 in untrained or trained respectively.
Yeah, I think it's just the fact that the highly trained use more of the cardiac output, more of their oxygen consumption devoted to the respiratory muscles is simply because their work of breathing is that much higher, because their ventilatory requirement is higher, because their metabolic requirement is higher. Is that okay?
Yeah, that makes sense. Another topic I wanted to ask you about, because I don't think I've understood it properly, it might relate to the intrathoracic pressures that you mentioned before. It's the concept of the thoracic pump, and the thoracic pump potentially assisting the heart in the work that it does, if I understood it correctly. Could you maybe elaborate on that concept?
Well, yeah, this is really a tough one to examine. We've done a few studies. Mamma Jordan Miller, who's now at the Mayo Clinic with us, and we're trying to understand how the pressures developed by a breath influence the output of the heart. Okay. That starts not just inside the chest, but also in the abdominal compartment, because the major vessels, femoral vein and everything that are popliteal vessels that are returning blood flow to the heart run through those compartments. And even in mild exercise, we will produce positive pressures on expiration in that abdominal compartment. At the same time, we'll produce negative pressures within the chest during inspiration. And so you've got, and if you breathe primarily with the diaphragm, that's our major inspiratory muscle, when that diaphragm descends, it increases the intra-abdominal pressure during inspiration. So you've got different pressures here, and they all will have an effect on blood flowing through those compartments and returning to the right and then the left side of the heart. Okay, sorry, but it's just the way it is. In addition to that, you've got pressures developed around the heart. Okay, and these can affect the ability of the left ventricle to fill during diastole. Okay, so all of these factors. Now, do we haven't all worked out yet on how they affect venous return to the heart and cardiac output? Not quite, but I can give you some snippets. For example, if you put a person on a ventilator, and we used a ventilator for about 15 years to control the work of breathing at maximum exercise. A wonderful machine developed by Mamma and Eunice at Winnipeg years and years ago. Now it's used as called a proportional assist ventilator clinically, especially in Europe. They seem to like that ventilator there. It's beautiful. And I was the first one to go on this in our lab back, when was this? The mid-90s. And I'll never forget it. I was exercising very hard. We switched this. I'd already practiced getting used to it. I mean, you're having a machine ventilate for you while you're exercising. It's not the usual thing to do. But we had this sync to my breath. I would trigger it myself. It's not completely taking over your breathing, but it assists each inspiration. So I was exercising quite hard for me, and starting to feel my limbs getting tired, and having a perception of effort and dyspneic a little bit, short of breath, and they turned the ventilator on. And I think within a dozen breaths, all of a sudden I could feel my legs just so much stronger. I couldn't believe it. And I stopped the exercise, I rested for about an hour, went back in, tried it again. Same thing kept happening over and over again. And that's when we figured out that when you reduce the work of breathing and reduce the negative intrathoracic pressure, that a couple of things were happening. One, we were redistributing blood flow. And then we actually measured the blood flow to the limbs and found that it tracked the work of breathing. And then the other thing we found out was that when we reduced that negative inspiratory pressure, that reduced the venous return to the heart. So you actually had a little bit of a drop in cardiac output. So that just shows us, I'm sorry to go on and on with this, but we obviously don't have everything figured out, but
yeah,
I can say this, that the pressures we develop with a breath affect both the venous return to the heart and the ability of the heart to produce stroke volume.
No, that's really interesting, and I think the way you explain it makes a lot of sense, even though it does require a bit more investigation, I guess.
Oh gosh, yes. It's relative importance relative to other factors that determine venous return. For example, we have no idea. It's importance on inspiration versus expiration. There's a group in Italy that's suggesting that there's this reservoir of blood in the abdominal cavity that's recruited during exercise. I don't believe that. I just don't think it's large enough to play a role that the pressure developed there enough. But when they do experiments with extremes, they see this big recruitment of blood volume. And I think that's a little far, but definitely you affect both venous return, you affect the ability of the heart to fill, and therefore stroke volume.
Something else I wanted to touch on, we talked a little bit about this off air before we started recording here. So talk about respiratory frequency, tidal volume, and the implication of those two parameters for exercise and performance.
Yeah, first of all, the unknown part is we're not sure what mechanisms underline why we, quote, choose to use frequency sometimes more than tidal volume and other times use tidal volume more than frequency. We know why it's a good idea, but whether they're reflex mechanisms doing this, whether it's feed-forward mechanisms doing this, whether it's those mechanisms related to the specific type of stimulus that exercise presents, I'm embarrassed to say that we do not. There was a big, in the Journal of Applied Physiology earlier this year, a group from, I think, the UK presented an opinion piece. Say we don't pay enough attention to what's happening to frequency and tidal volume. And this is a neat idea in that journal. In fact, I started when I was editor of it. That then invites the readership to write in. And I just was fascinated by the range of responses to this on such a fundamental question. Okay, so we to be figured out. But what happens with exercise is usually in a healthy person that when they start exercise, ventilation will increase in direct proportion to CO2 production, alveoli. That's why we control our arterial partial pressure of CO2 and the pH in the blood so precisely is this proportional increase in ventilation. So that's important, but how we do that is equally important. So a couple of things happen. One, in the early phases of exercise, it's both frequency and tidal volume, but it's mainly tidal volume, goes up usually. And that tidal volume is increased by doing two things. One, you recruit your expiratory muscles. As soon as you start to exercise, you recruit them. And you can see that because the lung volume that you start each breath from decreases. So you're increasing the tidal volume by both encroaching on what we call the expiratory reserve volume and the inspiratory reserve volume. That's so important because if you try and breathe, if you take a breath out and start each breath from way down here, it costs too much force to take that next breath. So there's a given part of what we call a pressure volume relationship that you want to remain on the linear part. And that's what this allows you to do.
Mm.
But you don't want to go too high on the inspiratory side, for sure, because now you'll get to the point where the lung becomes very stiff at high lung volumes, and you avoid that. And that's what healthy people do. They don't breathe at those extremes.
Mm.
Did anybody tell you to do this? Heavens no, except your brainstem. Okay. Now you're exercising harder and harder. Oh, the other good reason it's good to not use too much breathing frequency is each breath has dead space with it. Okay, the conducting airways are not going to move air through your alveoli where the gas exchange occurs. So you don't want too much conducting airway space, too much dead space.
Do you have an idea of the volume that represents? I read it was about 1/2 liter. Is that correct?
Well, that's too much.
Too much.
That's way too big. Yeah, in a normal sized male, for example, that might weigh 70 kilos, you might have less than 200 milliliters.
Oh, okay. So it's much less than. Yeah.
And right, and that's just in the conducting airways. The other kind of dead space is down at the alveoli, but in healthy people, that's immeasurable. It's so small.
Okay.
So our dead spaces are conducting airways. But each breath is going to contain that. So you want to keep the frequency to a minimum. And you do. But not when you get into heavy exercise. You don't want to get into those highly stretched regions where the lung becomes stiff. And so you limit the tidal volume. And now the frequency increases. So you give it up. You give up a little there. You give up a little dead space ventilation. But the dead space is a fraction of the tidal volume still is way, way down to where it was at rest, which is, so you really have the best of both worlds here to accomplish 100+ liters a minute ventilation by controlling the end expiratory lung volume, which also, by the way, controls muscle length. So you want a nice long length for your inspiratory muscles to generate all the force they're going to do. And we've measured, many years ago, how much of the dynamic capacity of your inspiratory muscles that, say, a non-trained person used at maximum exercise. And it's less than 50%. Think of all that beautiful reserve you've got. Now, in an athlete, that's different. The lung is not that different in the athlete than it is in the non-athlete for a given size. Unfortunately, that's too bad. The lung doesn't seem to want to train. It's not that the lung isn't adapted. Do you want to talk about that a little bit?
Yeah, I actually had a question on the lung itself for you. So maybe go on that, and I'll ask my question after.
Okay, but the idea about frequency, tidal volume, index per lung volume, etc. That's what I tried to address just a moment ago there.
Yep, that was clear. Let's maybe go on the. Let me just think. So we covered this. You just mentioned, maybe to finish on that, you mentioned muscle length and the effect on the efficiency of breathing, because as we know, like any muscle in the body, there is a range, or like you said, a length that allows for optimal force production. And so it's the same for the diaphragm. If it's maybe too relaxed or if it's too contracted, which are those kind of extremes of the spectrum of breathing in terms of volume, you're not as efficient as if you were kind of staying more in that middle range. Does that make sense?
Right. Very important to not just the diaphragm, but all the inspiratory muscles.
Right.
Remember, they're using a lot of them, as we said before. So when you do something just as simple as recruit the expiratory muscles with the beginning of exercise, and that decreases the end expiratory lung volume, you're now increasing the pressure in the abdominal compartment. That's going to push the diaphragm up, lengthen it a bit, right to its optimal length. So something as simple as, the other thing that recruiting the expiratory muscles means that you store that energy on expiration, and then on the next inspiration, that gives you kind of a passive assist to the inspiration, generate the negative pressure.
On the diaphragm and the other inspiratory muscles.
Yeah.
So it's like that. It's almost like you have after the inspiration, you get the elastic recoil of the rib cage, or the whole I guess
Absolutely. Yeah.
right. And then
Yeah.
the other way around, you get the elastic recoil of the, essentially like a stretch reflex you would have at the bottom of a squat, but with the diaphragm itself from
Yeah.
okay, that's really interesting.
Yeah, it is. And I mean, what a beautifully designed thing. And of course, lung tissue is highly elastic too.
Mm-hmm.
So as we sit here breathing at rest, we never use our expiratory muscle.
Mm-hmm.
Because at the end of every inspiration, passive recall will take us back to where we started without even thinking about it, right?
Mm-hmm.
Yeah.
Yeah, you said the lungs don't seem to want to train. So maybe elaborate on that a little bit.
Curious thing, isn't it? This is curious. So my personal history with this was that you were asking me a bit ago how I got interested in the respiratory system, and I was telling you about how perfect it was back in the first started to look at this, and I still believe that to a great extent. And for example, if you just look at the oxygen exchange by the lung, and you measure arterial blood in people who aren't highly trained, and you see that the arterial PO2 is controlled exactly at resting values. It never falls. You can exercise till you're falling off the device, and it's maintained. And you never see the CO2 rise. In heavy exercise, it's controlled perfectly at resting levels. During moderate exercise and heavy exercise, it falls. You get a hyperventilatory response. All good. In the early 1980s, and I can't even remember why now, we started to look at people who were really highly trained. So I think the first studies were done in the late 70s that we tried. And we had 2 Olympian 1,500-meter runners that were training for the Moscow Olympics, which unfortunately the Americans never ended up going. They boycotted. But these guys were training. And 2 of them were local. They were around Madison, Wisconsin. And so for this study, which is like I said, I don't remember why, we had them come in, put an arterial catheter in, ran them on the treadmill. And both of them were doing fine. And then they got into about 3/4 to their max and up to max. The arterial PO2 fell during exercise. I'd never seen this. Now, when I look carefully in the literature, you can see the odd example, okay, of one. Scandinavian literature had it. There was some study out of Minneapolis by Rowell that showed it, but he hadn't actually measured blood gas saturation. I thought, wait a minute here. Does this mean that the highly trained person will kind of outrun the lungs' ability to exchange gas? And we knew from studies done earlier in our lab, anyway, that we measured diffusion capacity of the lung in several different groups of athletes over a training session. And their VO2 max went up with their several weeks and months of training. These were intercollegiate athletes. But nothing happened to the diffusion capacity of the lung. And if you look throughout the literature, there wasn't a lot on it, but you could see athletes don't, you see the odd one with a higher diffusion capability in the lung, but it's not consistent. Well, if you have a higher demand for oxygen transport, but a major organ that delivers oxygen has not adapted, will it get to the point of failing as a gas exchange? Well, we went ahead and studied, I think, 20 of these athletes at the time, and a little more than half of them showed this hypoxemia. And so that's a long time ago, and that's now been confirmed. And we still don't know why some of them do and some of them don't. I wish I could explain that. If we had better methods of imaging the lung during exercise, the small airways in the alveoli, we could probably tell what's going on. But it's a matter of them not being able to distribute ventilation and perfusion perfectly in the lung during exercise. And when you have your muscles extracting so much oxygen and it comes back on the venous side almost completely desaturated, you better have a near perfect gas exchange system, and we don't. And it's the fact that the cardiovascular system and the locomotor muscles and the red cell mass has beautiful adaptations to training, gorgeous, but the lung doesn't seem to want to train. Okay, it's not that the lung isn't adaptable, If you look at people born and raised in high altitude, the lung grows in hypoxia, at least in maturing animals and people. We studied the natives of Leadville, Colorado, 3,100 meters. They'd only been there 3.5 generations when we studied them. Paltry compared to Swiss or people living in Tibet or Ethiopians or Peruvians. Tibetans have been there 30,000 years. Peruvians, 10,000 years. So this was peanuts, but their lungs were unbelievable.
Can you give an idea of the increase in? Could you give an idea of the increase in the lung, I guess, volume or lung size?
No, not volume so much. I know that's in the literature. Volume. It wasn't volume so much. It was diffusion surface.
Oh, okay.
And when that's studied in animals, where you can look at the more detailed morphology of lung, it's the number of alveoli and the number of capillaries. Now we have 300 million of them ourselves, but this has even more. 20 to 40% increase in diffusion capacity of the lung at rest and exercise. And they exchange oxygen from alveolus to blood so much more efficiently than we do. And they hyperventilate much less during exercise. So pretty ideal adaptation if you're living in a hypoxic environment.
Right. Is that something that can be changed within a lifetime, or is that a generational thing where you essentially have to be born with the genetics of your ancestors having, I guess, evolved at higher altitudes for, a certain amount of time to benefit from those, I guess, genetic predispositions?
You do not. If you move there during maturation, the lung matures up into adolescence. It's got a long growth period. Unfortunately, it starts to decline in our late 20s. Isn't that terrible? So what a terrible thing to do to humans. Anyway, you can see this. You can take a young animal from sea level and shortly after birth move them into a hypoxic environment. You'll see this, just like we saw in the humans of Leadville, that those that were born at sea level moved with their parents to high altitude as children show this very similar adaptation and diffusion capacity. So the lung will adapt. If you do what's called a pneumonectomy, take out part of the lung and look at adjacent areas of the lung, you'll see growth, substantial growth in a fairly short period of time. We know in small animals, if you change their nutrition, starve them, the lung will be affected by that. So it's not that the lung is not adaptable, but to the exercise or so-called training stimulus, it doesn't seem to be. Now I'm seeing some stuff more recently on, just saw an article out of Poland in mice, training mice and seeing the volume mitochondria in the lung, not the muscles, in the lung actually increasing. I thought that was really interesting. I don't know what it means to function. I have no idea yet, but I thought that was interesting. I see another one in which rodents were made to smoke cigarettes. And then they saw deterioration in diffusion surface of the lung and in lung function. If they trained those rodents, but kept them smoking, we do crazy experiments. You can see that this deterioration in the lung diffusion was actually constrained a bit by the training.
Okay.
Well, I know those are a little far out kind of things, but it's an idea that there might be something and we know now, beautiful work from Denmark over the years, that contracting muscle is an endocrine organ and it produces cytokines. We always thought those, like IL-6, for example. We always thought those cytokines were harmful. Well, maybe some extent, but there are also a lot of benefits of these cytokines. And now that's being explored in treating cancer with exercise, all these ideas. And it could be that might also, the training the locomotor muscles might also have an effect on inflammatory responses to the lung. I still haven't seen any really good evidence, but that has to be investigated in health and disease.
So sorry to cut you off. So from what you said just before, there is a pulmonary diffusion limitation that does exist, and the only
Yeah.
way to combat that is to move at high altitude when you're a child, and then grow up there. Would that be kind of a way to put it?
Yeah. And some people have wondered why. You remember who did so well in the Mexico City Olympics at 7,500 feet?
I don't.
Kenyans.
Oh, right.
It's the
Because
first time, yeah, you're too young. It's the first time we heard of the Kenyans.
yeah.
And what I remember the best is that the Kip Kenyo from Kenya
Mm.
beat by at least 20 yards the American record holder, world record holder in the 1,500 meters. And
Yeah.
that was wrong. And the marathon was won, I think, by, I can't remember, it was from a high altitude country. And I just wondered, now, does it help you as an athlete compete at sea level? Well, maybe. But it certainly helps you if you're competing at high altitude, for sure.
Right.
Can't say for sure, but I would say yes. If I don't know of any other way to increase the diffusion surface other than to expose people to hypoxia. Now, that's going to come with a price, because oh, this is really getting broad now, but
I like it. Go for it.
okay, so hypoxia, we talked about the good thing that happened. The lung adapts very nicely. You increase red cell mass, right? That's good at high altitude. You don't have to train, just go there. And but there's some downsides. One, your pulmonary vasculature constricts at high altitude. Did you know that?
I did
People
not.
don't appreciate that. It makes no sense. It constricts in the fetus because our lung's not aerated in the fetus. So you don't want the blood flow through the lung. And it doesn't. It goes through the chambers in the heart that flows at birth, right? Okay. But when we're born and now our lungs being aerated, it'd be good if we didn't have that hypoxic vasoconstriction in the lung anymore. But it's still there.
Do you think that
You want me to tell you why, but I don't know why it persists.
maybe
Makes
not?
no sense at all.
Maybe you don't know why, but do you think that potentially, if my line of reasoning makes any sense, would the vasoconstriction of the pulmonary system trigger an increase in diffusion capability of the lung to make up for that lowered perfusion? Does that make any
Not
sense?
that I know of. Not that I know of.
Okay.
I don't know, and I don't know how you'd ever study. Well, you study that in an animal model, but I don't know of any evidence that indicates that. What it does do, that you're trying to think of the good side of it.
Yes.
Because you're thinking teleologically. If it happens, it must be good. It's okay if you stay at sea level. It's not, you're going to be okay and stay healthy. You don't smoke cigarettes, don't get interstitial lung disease, don't get chronic obstructive pulmonary disease. That'll make you hypoxic and trigger the thing at sea level, right? Because you're hypoxic, which is not, it's never, we won't get into why that can be good and bad, but it's not good. You get pulmonary hypertension, the right heart fails. Okay, so if you live at high altitude, that pulmonary vasoconstriction, and we learned this way back in the 60s from cattle that lived and grazed in Colorado, and they get a thing called Brisket's disease. And it's a normal biological adaptation to their hypoxic environment. These vessels constrict. The right heart has to work against, and it swells, and the right heart gets huge, okay, and fails. And so that's what you pay for living at high altitude. You may increase your diffusion surface, but you're going to have a negative effect on this remodeling your pulmonary vasculature. See, the pulmonary vasculature, all the cardiac output passes through the lung. No other organ in the body gets all of the cardiac output, but the lung does. It has to be oxygenated, right? So you want those vessels to be highly compliant, low resistance. The blood pressure in the pulmonary arteries, 10 millimeters of mercury. In your aorta, it's 100 millimeters of mercury. So you can see the difference in vascular resistance. Yeah, it's low in the lung. You start to increase blood flow through the lung. You get up and walk around. Those vessels just are as compliant as can be. They open up. You don't want the pressure to get too high. And it doesn't, unless you're constricting it. And so living at high altitude does that. My advice is stay where you are. Stay nice and close to sea level.
Can you talk about other potential negative adaptations of hypoxic environments to the whole respiratory system as it pertains to performance in sports or exercise?
Yeah. Another aspect would be hyperventilation. Okay. So when we go to high altitude, within seconds of exposure, we start to breathe more. And the longer we live there, over a period of weeks, our chemoreceptors keep increasing sensitivity. They do it within the first couple of hours, they keep increasing. And so we ventilate more and more. Is this a good idea? Of course it is. You're decreasing the inspired pressure of oxygen, but you're going to increase the alveolar pressure of oxygen by bringing in more air. Okay. So that's an important adaptation. But at the same time, the work of breathing is higher, especially during exercise. So that's why you run up a hill when you're at 10,000 feet and oh, wait a minute, I'm breathing more. I never felt that at sea level, right? Do you live at high altitude in Switzerland?
I'm by the lake, but I've been in higher places, and yeah, like you say, you feel it right away.
Sure. And we know that, especially in, say, an athlete who really has to ventilate a lot because the exercising hard on altitude, they decrease their max VO2 by even less than 1,000 meters altitude. You start to see the reduction. They respond very poorly to high altitude. And okay, so that's another thing. The other thing is diffusion limitation occurs when you're in a hypoxic environment much more readily. So you get hypoxemia. And again, the high athlete is the greatest example of this. That article I sent you has that detailed in it, that the Gore in Australia exposed highly trained athletes to 600 meters altitude. That isn't even a hill. It's just a hill, it's not a mountain. And their desaturation was really exacerbated in their arterial blood. And of course, their max VO2 is going to be compromised. And so those are some of the things. So high work of breathing, high pulmonary vascular resistance, desaturation because of diffusion limitation, those occur in a hypoxic environment. Another one is that, and all of these are adaptations, but they're maladaptations as well, and it's how they balance one another. And another one is red cell production. So a common problem people living for long-term at high altitude is an overproduction of red cells. So a little bit's good, but an overproduction is too much. And finally, another one is high levels of sympathetic nerve activity. These chemoreceptors I talk about get revved up, and that's good because you ventilate more and you protect your alveolar PO2. But your sympathetic nerve activity also increases, which produces systemic hypertension. So you can see it's a pro and con. It's, I know that a lot of people that study high altitude preach the benefits. And there's even a whole, you're a trainer, and you've heard of hypoxic training.
Yeah, I just read a book, and about half of it is dedicated to simulating high altitude training with some breathing protocols. So it's really interesting that you're talking about all that.
Oh yeah, I just participated in a debate where we took the negative side. Do not train in hypoxia, and don't do the sleep high, train low, either one. And the other side, the French group who believes strongly in this, took the other side. You can read it if you want. It's in a journal called Medicine, Science, and Sport of Exercise, MSSE, of the American College of Sports Medicine. Journal.
Great. Thanks for sharing the reference. I'll dig it up and put it in the show notes. Going back to our conversation on the lungs, are there any, and you mentioned prior as well, the upper airways that do become, let's say, a morphological limitation when it comes to high rates of breathing? Is there, besides the lungs and the upper airways, are there any other morphological limitations to the respiratory system for
Yeah,
exercise.
the pulmonary vasculature.
The pulmonary vasculature. Okay.
Yeah.
So those would be
Um,
the three areas that limit performance or absolute output, and that we don't have an influence over. Is that correct?
right. And then the fourth one would be the respiratory muscles.
In what sense?
Because if you fatigue them, then you'll activate the metabolic reflex and redistribute blood flow.
Mm-hmm.
And you can show that by using that ventilator I talked about before.
Mm-hmm.
You can improve performance by decreasing the work of breathing during exercise.
Mm-hmm.
And we think the major reason the performance is improved is because of blood flow redistribution. So that's another area of limitation.
Right. I read that females were more prone to respiratory limitations due to essentially the size and the makeup of their lungs. Is that correct?
Who?
Female athletes,
Oh, yeah. That was suggested a long time ago by not so much for exercise, but just a sex difference by famous guy at Harvard University, Jerry Mead. And in the 90s, we did some studies on female runners, highly trained endurance runners, and we found that at a given level of ventilation, they got into flow limitation much earlier and lower levels of ventilation than did men.
Okay.
And we could relieve that by having them just breathe helium, which increases the flow volume, max flow volume envelope. And so, and now Bill Shield, a former student of ours at University of British Columbia, has followed up on this. And he's done a lot of imaging studies on the airways of women and men, healthy, and finds that there are certain lobar levels, those are large airways, that are narrower in women than they are men. So 2 or 3 morphological studies have come out in the last year on that. And so this can, if you have narrowed airways, then you're going to have a high resistive work of breathing. It's a fundamental law, gas law. And so, and indeed that's true. And so the airways of young adult women, and it seems to occur in pubescence. As they approach adolescence, this is where the difference between men and women's airways seems to become clear. But still, you know, it's early days with this. But it looks like that's true. And like, for example, what does that mean to aging, this long ages in men versus women? We don't know that yet. But you could predict that the women would be much more affected by that. Yeah. So yeah, it looks like there's this next difference there.
So we talked about hypoxia, so the lack of oxygen. Can you talk a little bit about CO2 tolerance and its effect on health and performance?
Yeah. Well, normally when we exercise heavily, we start to produce lactic acid. And the pH starts to become acid in the arterial blood. One of the so-called compensatory mechanisms for that is that we hyperventilate. Our arterial CO2 falls. So that means we've increased alveolar ventilation out of proportion to CO2 production.
Right.
So that's different than mild or moderate exercise. Okay. That helps to compensate for the pH. So the pH isn't as acid as it would be. So that's a normal response that happens. And there are lots of mechanisms for that hyperventilation. One of them probably is the acidity stimulating the peripheral chemoreceptors. Okay. Now let's go to the highly trained athlete. And we see that a lot of them hyperventilate in heavy exercise too, just like untrained people do. They're at a much higher level of CO2 production and they're a higher level of ventilation, of course, but they hyperventilate. But some of them don't. It's not that they retain carbon dioxide above resting levels, they just don't decrease it as much as one would normally do. And if you don't hyperventilate as much, it means that you haven't increased your alveolar O2 as much. See, when you overventilate, or when you ventilate, you're regulating both your alveolar oxygen and your CO2 reciprocally.
Mm-hmm.
One goes up, the other goes down. It's identical mechanisms. Okay. And this is one of the reasons that athletes get hypoxemic during heavy exercise, because they don't raise their alveolar PO2 enough. The other reason is the difference between alveolar and arterial PO2 is too wide. The lung isn't exchanging gas as well. Okay. So why don't those athletes hyperventilate during heavy exercise? Well, one of the reasons is mechanical limitation that we talked about before. Okay.
Is that primarily on the expiratory musculature that might be fatiguing?
No, yes, yeah. No, careful. It's not a muscle limitation. It's an airway limitation.
Right. Sorry. So the upper
demand for flow rate exceeds the airway's capability to handle it. And on expiration, you actually see the airways dynamically compress. The pressure outside the airways exceeds that inside. You dynamically compress the airways. You get to the point where you're producing more force, but you're not getting more airflow. Highly, highly inefficient. That's where a very high expiratory work of breathing comes from. Okay. So one of the reasons that the hyperventilation is not as it should be in heavy exercise in the highly trained athlete is a mechanical limitation. Okay? But there's some athletes that even though they are not at the limits of their flow being mechanically limited in their airways, still don't show this hyperventilation. And they could be in a group where the receptors responsible, chemoreceptors responsible, are just not sensitive enough. And so you call this CO2 tolerance. I guess that's a good enough term for it. So it's probably not just the chemoreceptors that are doing it. It's all the receptors that are involved in the hyperventilation of heavy exercise, of which there are many, most of which we don't completely understand. So I guess that's what I could say about that.
Yeah, that makes sense. And so would you say then that, because there are protocols out there that are starting to become popular in the training world about trying to increase your tolerance to CO2, because but just like you said, maybe having a very low tolerance to CO2 isn't great because you maybe start to hyperventilate too early. But then on the other side of the spectrum, like you said, it's all about kind of that middle range. And if you go too far into, let's call it CO2 tolerance training, then maybe you're too desensitized to that drive that would come from the different receptors, and then you're not responding proportionally to the increased demand in respiration. Does that make sense?
Yeah, I guess it does, but you'll have to tell me more about CO2 tolerance training. What do people do? Do they ask the athlete just to underbreathe and retain CO2 while he's training?
So it can be done at rest. It can be done during training as well. But essentially, there's that book called the Oxygen Advantage by a guy called Patrick McEwen. It should really be called the CO2 Advantage. It's really a misnomer, the title that he picked, because he essentially puts forward the benefits of higher CO2 tolerance in the sense that of lower breathlessness, especially for untrained people. And what he uses, he calls that a BOLT test. I think it's an acronym for breathing oxygen limit test. Honestly, I forget the exact meaning of the acronym, but essentially what he says is sit down, breathe through your nose, and then on a normal exhale, just pinch your nose, stop breathing, and see how long it takes for you to have the first reflexive intent to breathe in, whether it's diaphragm contracting or the need to swallow. And it gives you a score on a scale of, it's in seconds, so you count in seconds until you get the first reflexive drive to breathe. And what he talks about is if you're under 10 seconds or thereabouts, you have very poor tolerance to CO2, and you would benefit to increasing that towards the 20, 30, 40 mark, so that you essentially, I think what he's getting to is that by increasing your CO2 tolerance, you reduce the propensity to hyperventilate early and to be maybe, if we can say that, triggered by higher levels of CO2 accumulating in your system. And then he taunts the benefits of higher CO2, or how to say that? Yeah, higher CO2 level, which would impact your ability to extract O2 at the muscle, and also talks about nasal breathing a lot. So that's kind of the angle, if that makes sense.
Boy.
What's your take on that?
Is he actually studied it?
He cites a lot of studies, but I don't know if he's studied. I mean, I don't want to speak for him, so all I can say is that it's a fairly popular book in the training world, and it's getting more and more visibility. So yeah, if you have maybe a response to my perhaps incomplete summary of the idea, but what's your hot take on what I just said?
So he has the people learn to tolerate breath holds, kind of.
Yes. Yeah, that's
underventilation.
Yes.
So, and the goal being to prevent hyperventilation too early.
Yes,
right?
and also he also talks a lot about the negative effects of mouth breathing, especially at rest, and the importance of nasal breathing. He talks about NO2 and obviously conditioning the air coming into the lungs when it comes to temperature and all those things. So that's kind of essentially, he talks about the downsides of overbreathing is really one of the main
downsides of what?
Overbreathing at rest, which from his theory would drive CO2 levels to lower levels than would be ideal, which then affects extraction dynamics, let's say at the muscle from a shift in the oxygen dissociation curve.
Wow. Holy cow.
You don't seem convinced.
Well, number one, let's see. Nasal versus the low. There's both a mechanical. I mean, we breathe nasally and we breathe orally automatically.
Mm.
And the higher resistance route to breathe is nasally. Okay.
Mm.
So that but at rest, when you're moving 6 liters of air per minute and your inspiratory flow rate's about 0.5 liter per second, it doesn't matter that you're breathing through a fairly narrow airway because the resistance is just so low.
Mm.
Or that the demand is so low, excuse me, for flow. As soon as you start to exercise, you switch from a primarily nasal, primarily oral breathing route in a human. Not completely, but primarily. And this is good because you're using a higher diameter airway and lower resistance. And we don't have to be told to do this. It just happens. Okay? So reflex effect that happens. Now, as far as humidification, so you don't have to teach anybody to breathe through their nose or through their mouth. They're going to do it in proportional systems. Unless they have, an anatomical problem, which several people actually do, with the nasal passages and the way they're arranged. But ordinarily speaking, this is just going to happen normally, and the appropriate thing happens. When you exercise, the flow rate demand increases. You're going to breathe primarily orally. Now, as far as humidifying and the air, in an untrained person, the flow rates, you can get to the point where you start to dry out the airway a little bit and cool it. Mm. Even some of the major airways, which we found this out a couple of decades ago. In a person with a normal airway, it's not going to do anything. In a person with a mildly asthmatic airway, it can cause airway constriction, smooth muscle constriction, the bronchi. Mm. And in a highly trained person who reaches really high flow rates, we see a lot of this. There's another example of reaching too high flow rates on intrathoracic. And of course, there's extrathoracic airway problems we found out now too. Mm. So, but I can't really think of why on earth I'd want to have somebody adopt nasal breathing under high flow conditions. Be honest with you, any flow conditions. Mm. So now the CO2 tolerance thing, well, we never retain CO2 during exercise anyway. Nobody does. And as an asthmatic athlete, but I've seen that in some asthmatic athletes, or people with chronic obstructive lung disease, or thoroughbred horses. Mm. Oh, by the way, the thoroughbred horse, yeah, they are the prime example of the lung as the limiting factor to exercise. Mm. Their small gene pool, like 6 Arabians, 17th century, right? They all come from that. Yeah. And 6 Arabian horses. And their lungs are so underbuilt for the 500 liter a minute cardiac output and the 1400 liters a minute ventilations that they have to reach. So if you look at a horse, if I can take that example, they, on each inspiration, they're obligate nasal breathers. On each inspiration, their nares collapses because the pressure generated. So that's terrible. I mean, the work of breathing is out of sight. Mm. Their PCO2 is not 40. That's normal. Okay, yeah. It's at the rest. At heavy exercise, it's in the mid 50s. So they retain CO2, but nobody else does. Nobody else does in health. The idea that if you do retain CO2, will that affect oxygen extraction? Of course it will, because if your CO2 is high, your alveolar PO2 is low, which means your arterial PO2 is low, which means your saturation is going to be low, your content's going to be low, you're extracting the same amount, blah, blah, blah. Okay. You won't be able to extract the same much because your arterial O2 content is lower. Mm. But it's not the CO2, it's only as it affects the O2. Mm. But I guess to me, but I'm ignorant of it because I don't know the details in what you told me. I can't think of any reason why you'd want to do that. Any reason at all.
You'll give me your address after the call. I'll send you a copy of the book so you can make your an educated guess on it, I guess. Sure. So maybe,
and especially if there happen to be any actual studies done on that, I'd love to see that.
Mm-hmm. Yeah, I'll definitely send you what I have after the call.
Okay, great.
Before we move forward, I have a few non-respiratory related questions for you, but maybe to summarize what we've gone over, maybe can you go over what are the primary limitations of the respiratory system during high intensity exercise for humans?
Okay. In a non-trained human.
Let's talk. Yeah, you know what? Do both. That's probably a good idea.
Okay. The only contribution I know of the respiratory system, the limiting exercise performance in an untrained young adult, let's say.
Mm-hmm.
So that's important because the aging is a big factor we haven't talked about here, but it's a huge factor. In a young, untrained young adult would be the work of breathing. It's always going to be significant.
Mm-hmm.
And so if you unload the work of breathing, they do an experiment, unload the work of breathing with a ventilator, they'll work a little longer. Okay. But in a non-trained healthy person at sea level, again, you don't see hypoxemia, so it's not going to be a factor.
Mm-hmm.
You don't see the pulmonary vascular pressures reach a high enough level that they're going to impede stroke volume, so that's not going to be a factor. You see very little evidence that the intrathoracic airways are cooling to the point where you get exercise-induced asthma, unless you're way out on the allergic, talking about.
Mm-hmm.
There's no evidence, very little that I can see, what we haven't investigated, of the extrathoracic airway, the glottal airway, that in the highly trained athlete, there's a high prevalence of obstruction in that airway. But that's at very, very high flow rates.
Mm-hmm.
And so again, in the untrained person, this would probably not be a factor. As the cardiovascular and mitochondrial volumes and skeletal cardiovascular system, total circulating blood volume, total circulating red cell mass, mitochondrial volume, skeletal muscle, left ventricle, these all train. They're all trainable.
Mm-hmm.
And there's certainly probably a genetic component in this as well. So Olympic athletes sort of thing. But the respiratory system's trainability is not as great as those other systems. So the VO2 max increases, but the respiratory ability to contribute to that is constrained in the highly trained, relatively speaking. Okay. So what you see in the highly trained to contribute a respiratory limitation is arterial hypoxemia. Okay. And again, the prevalence of this, I guess we've studied enough now that it's, I don't know, is it maybe half of these highly trained athletes, maybe a little more, contributes. And it's not just, by the way, the drop in arterial PO2. It's the drop in an arterial PO2 combined with a rightward shift in the dissociation curve because of the acidity and the high temperature. So the two contribute equally to the desaturation you see. So and once you desaturate more than about 3%, you start to see an effect on the VO2 max.
Right. So
the biggest effect you'd see in an athlete of this is probably about 15%.
On their VO2, right? So you said the right shift in the oxygen dissociation curve. So that is not due to, because what I read and what I retained was that, at least from the training literature or training, I'm not going to say literature necessarily, but the training stuff that I read is that the right shift was induced by an accumulation of CO2. But you mentioned heat and acidity as being the driver of that rightward shift. Is that,
right.
Is that
metabolic acidosis?
Right, but so it's not
CO2, CO2.
It's not the accumulation of CO2 that triggers the right shift in the oxygen dissociation.
Careful. In arterial blood at the lung.
Okay.
Right. In the venous and muscle capillary blood, huge. PCO2 is 80, 85 millimeters of mercury.
Okay. So
it contributes to the right shift there. People oversimplify this shifting of the curve.
Yeah, that's what I'm realizing. Yeah.
Because there's an index called P50. It's the partial pressure of oxygen, 50% saturation. But there's very, very little relevant blood that operates at P50. The arterial operates at one section, that unloaded at the muscle operates at another. And it's absolutely crucial to consider where this is happening. So, yeah, it's a metabolic acidosis shift and a temperature shift, okay, in arterial blood. Okay. So, desaturation is the one thing. In the highly trained, we're talking about.
Yep.
Okay. And this is especially true at even mild altitudes in the highly trained. Okay. The second is the work of breathing, because now the work of breathing is 15–18% of the VO2 and the cardiac output. And at least studies we've done, and now some others, took a number of years to get. It's so hard to measure muscle blood flow, do it accurately. Okay, and you have, it's a highly invasive study, and we did it with thermal dilution back in the late 90s. I mean, those are, and then we did right heart catheterization. I'll never do that again. That really scared me in healthy people. I know people do it. That's okay. We did it in 8 subjects, 16 experiments, and I was never so nervous about human study in my life. But the catheters floating up there in your pulmonary artery, the right heart. And anyway, so yeah, so the very high work of breathing, especially in sustained exercise, causing an increase in sympathetic nerve activity, probably because of this metabolite reflex, causing high sympathetic nerve activity, vasoconstriction in the limb. Plus, plus it'll add to perceptions of breathing, which, dyspnea to a certain extent, especially in prolonged heavy exercise. Okay, so there's the hypoxemia, there's the high work of breathing, redistributing blood flow. There's the high flow rates affecting both intra and extrathoracic airways. And that's mainly an athlete thing, where those flows get extremely high. And that's detailed in that paper I sent you. And then the other one, which is so new and so fascinating, is the pulmonary vasculature. That the cardiac outputs get, that the lungs' ability to recruit vessels to dilate is very limited compared to, say, skeletal muscle during exercise. It works greatly up to cardiac outputs of 15–18 liters a minute in on-train. But when those cardiac outputs, and remember, it all has to go through the lung, get to 25, 30, 35 liters a minute, what Lagersh in Australia has shown, that these pulmonary arterial pressures now exceeding 40 millimeters of mercury in a lot of these people. And now the right heart becomes the limiting ventricle in exercise. And he studied these people training over time, and he sees a thickening in the right ventricle. My goodness, that's supposed to be such a low resistance, high compliance system in the lung vasculature, that this should never occur, but it does. And he's now looking at the pathophysiology of that. What might that cause, other than it causing a respiratory limitation to exercise? What might it do? And he's seen some effects that are very bothersome about cardiac abnormalities, cardiomyopathies, in these kind of athletes. And it all starts because the lung vasculature does not adapt to training in a way that handles the high flow rates. It adapts by strengthening a muscle, the right ventricle. Okay, that's not great. That's not an adaptive response in a way. It is in a way, but it's maladaptive.
Maladaptive,
yeah. So those are I think I've covered them all. Those are the major limiting respiratory factors that occur in the highly trained.
And now, from your...
having said that, let's realize that still, in my mind, the major limiting factors to, say, the VO2 max is stroke volume. Okay, and that's primarily determined by you even know all the factors for that. But the respiratory system is just, I didn't mention that, those high expiratory pressures have an effect on ventricular filling and will affect stroke volume. But it's one, I think, relatively small contribution. So the respiratory system contributes to performance limitation, but it's still relatively small compared to, let's be clear on that.
No, that makes sense. So from your...
Is that okay?
Yeah, that's good. From your knowledge...
It's only in the It's only in the equine athlete where the lung is clearly the dominant limitation to performance, to oxygen transport and performance. And in the highly trained human athlete, when he goes to even moderately high altitudes, that the lung is the major limiting factor. Okay? The respiratory system can contribute to limitations at sea level in the highly trained, but I don't think we can ever show that it's ever the dominant limiting factor.
That makes sense.
Okay.
To your knowledge, what aspects of the respiratory systems can then be trained? We talked about the non-trainable parts. What can be trained?
The respiratory muscles can certainly be trained. And you can train the athlete who does endurance training, those muscles will train. And that's been shown, especially in the rodent model, by taking out the diaphragm and respiratory muscles and show that they increase mitochondrial volume, they'll increase aerobic enzymes, they'll increase capillary density, all the same things that occur in locomotor muscle. You have to work them a little harder because they're not as fatigable. But yeah. So as far as I know, that's the only trainable part of the respiratory system. The control of breathing, it doesn't seem to change much with training. It's already damn near perfect in untrained people. Yeah. So it's and we did talk a little earlier about the role of cytokines produced by the locomotor muscles and how they might affect the lung. For example, I gave those kind of far out examples of the smoking mouse and the mitochondrial volume change in the lung in training in mice. But we also know that if you take people with mild asthma and put them on a mild aerobic fitness program, not intense, but mild, that the airways seem to become less reactive. Okay. That's an area that, because asthma is treated so badly pharmacologically, the treatment of asthma is a mess. And it would be great to have more studies, definitive studies done with really good invasive measurements, imaging, immunology, on exercise training in asthma. I'd really like to see that. Of course, I need to mention that if you look at the prevalence of asthma among Olympic endurance athletes, it's extremely high. So again, there's the whole idea of the underbuilt intrathoracic airway handling those flow rates. Now, there's additional things there too. Training in chlorine-dense swimming pools, not good for the lung. Cross-country training in dry, cold air at the levels that those people train at. There's a study done in Norway, as far as I know, it's never been repeated, where they looked at airway biopsies of these athletes. They become asthmatic as they train. Call about maladaptation.
Right.
But why, if you use low-level endurance training in the mildly asthmatic person, why does that seem to work? I'd really like to see that studied. That needs to be a real good look at it. So there's another example that maybe I want to be careful of not oversimplifying that training never affects the lung. There may be these hidden gems in there. And I know the people in Copenhagen are starting to look at COPD and training at a much better way than it's been done before, and the role of these cytokines liberated from contracting locomotor muscle. Big area that needs to be investigated. Effect on the aging lung. Like, for example, we did a study, it's small, 17 subjects studied between marathon runners between the ages of 68, I think it was, and 76, longitudinally. We looked over time. And they continued to train. Because if you look cross-sectionally, you see, oh, there's a large number of these older athletes looked like their lung function was better than the untrained older athlete, okay? It's still pretty crappy compared to a 25-year-old. Aging has a huge effect on elastic recoil of the lung and on diffusion surface. It's huge. But when we looked over time, we saw that, yeah, their VO2 max fell like you'd expect at that advanced stage, but much less than in an untrained. But their lung deteriorated, their lung function at the same rate as an untrained person. Very disappointing, very disappointing. And I would really like to see that followed up more with really good measurements of lung function, lung morphology. Our study was a very small one. It's quoted all the time because it has to be longitudinal though. You can't look cross-sectionally at athletes versus non-athletes because you don't know why the athlete brought that lung to the event, right? I mean, that's, in fact, that's more likely than unlikely. So, yeah.
A couple other questions for you today, Jerome. The first one I want to touch on, I know it's a topic that you cherish, is the role of mentorship in research and then in life at large.
Oh my goodness. Yeah. Well, I can say that the, 4 or 5 or 6 key mentors that I had made all the difference in my life. Mike Uhas, he didn't even know he was mentoring me. I don't think, but he did. Brian Sproul made the same thing when I see him years later, and I got a nice award that they give to old guys if you hang around. And I was out in Vancouver and I was being introduced, and I looked down and there's Dr. Sproul. And I almost came to tears just to thank him. And he came after and he said, Jerry, I really didn't do much for you. But you see, he did just by being him. And then Dr. Rankin, when I was younger, maybe it's carried over even a bit to the older age, I got in a fair bit of trouble scientifically because I shot my mouth off a lot and I questioned a lot and got involved in some 1 decade-long controversy, very, at the time, pretty popular question that we kind of showed wasn't true. And so, but Dr. Rankin always defended me. And he always said, okay, yeah, they're beating on you and you shoot your mouth up too much, but, hang in there and keep questioning it. That kind of mentorship is so important. And so I wasn't a very good mentor at the beginning. I was so driven and so intent in these controversies I got involved in that I can remember examples I'd give anything to have that opportunity to mentor that young man or woman again. And I've apologized to these people since then. It's too late, but I did. But I got better over time because I saw other people that were so important to me. Hey, just the example of a mentor is a man by the name of Vladimir Fensel, now dead this past 10 years, at Harvard University. He wasn't even a full professor there. He was a refugee from Czechoslovakia. Man, this guy knew acid-base status. And that's a very difficult topic, very complex. Better than anybody I knew in the world, both applied and basic. And when we got involved in this big controversy, we couldn't get papers published. Nobody believed us. He hung in there with us, and he would mentor me from afar. This is before the internet. Nobody talked like this. It was on phone. It was by handwritten letters. It was, that kind of thing. And it got to the point where he even repeated our experiment, showed that we were right to that extent. But it was his mentoring over the phone, and not just on science, but to try and let these controversials get personal. That's so important. Science has to remain objective. My gosh, in the US, we've seen plenty of examples of this in the past. I'll be precise, 4 years, where science is denigrated to the fault of all of us, for God's sake. So he taught me that. So I think this is really important, and I've learned, and so mentoring has really become, I think, the most important part of my job. It's not that the science isn't. I mean, that's your common denominator you have with the mentee, and that has to be good. Another part of mentoring, tried to get involved in the social enterprise in our country and throughout the world. I found I involved in the 60s with anti-war movements and anti-racism movements, and they're very important, and there are a lot of people that are really good at them. And my heroes like Martin Luther King and Bobby Kennedy were great at that, and I admire them. But I tried it, but I wasn't very good at it in a group. So I started to mentor children without fathers through programs. And now, in the past year, I've gotten involved in mentoring ex-convicts. And this one-on-one relationship you get with people can really be important, both to you and to the mentee. So I'm a big believer in mentorships, and I'm a big believer in young people starting their careers, grabbing on to people. One of my guys scientifically was the late Bengt Saltine. I'm sure you've heard of. He's probably the world's best exercise physiologist ever, and trained more people from all over the world in Copenhagen than anybody did. And I remember running into him in the late 60s at a meeting, and he was giving us one of his new theories, and I told him I didn't believe it. I said, that's ridiculous. It doesn't certainly apply to the respiratory system. We became fast friends for the rest of our careers. And he wasn't a respiratory guy, but if I had anything in the exercise field where I really wanted honest, learned, educated feedback, I got a hold of him. And so he wasn't a formal mentor of mine or anything, but he was always there. And the conversations with him were absolutely wonderful. And certainly dictated. And the other mentors I've had are people that I disagree with. And several of them still think I'm nuts about a lot of our ideas. And they make you do your research better. Because, okay, you may have finished that experiment. You think, yep, there's the answer. Then you think, oh, wait a minute. What would Magda Eunice in Winnipeg say? Or what would Tom Hornbein out in Seattle say? Or John Severinghau say? So you go back and you do a few more reproducibility experiments, or test your hypothesis a different way to make sure. So those guys drive you too. And you become fast friends with pretty well all of them. Some you can't quite get to that point, I must admit, but pretty well all of them.
If you had a piece of advice for those listening, maybe a two-part question. Part one, how to be a good mentor, and part two, how to be a good mentee.
Oh yeah. Let's start with the mentee. I think how you choose your mentor is really important. Just because you happen to be, say, at your local university, the world's your horizon. Go for it. What you see in the literature, what you see at a meeting, what you hear from other people around you about good mentors. Don't limit yourself. Go for it. I remember when I first came to the University of Wisconsin, I couldn't believe it. My God, I must have done 5 seminars a week. And I got to the point where I said, gosh, I want to ask that guy some more questions. I was 22 years old or something and didn't know what the hell I was talking about. And I found out that these people want to talk to you. Scientists love to talk about their work, ad nauseum sometimes. And so I started knocking on doors, and I haven't stopped. I haven't stopped. And the older I get, the more brazen I get about asking fundamental questions. I'm not afraid to anymore. I don't care about my reputation much anymore. And I'm not submitting grants anymore, so I don't care who I'm talking to. I really don't. Another part on yeah. So that's what I would say to the mentee. And then, yeah, you don't do everything your mentor suggests you do, but you count on him and or her, and you um, well, about 7 or 8 or 9 years into my career as a scientist, nothing was going right. Experiments were failing. The questions I was asking were stupid. I was looking for quick answers to things, and I resigned. I resigned from my assistant professorship at the University of Wisconsin. And I was teaching medical students at the time, and I decided I'll go to medical school. That's a lot more straightforward. Just go and treat somebody. Don't you worry about coming up with hard and good questions and what new methods you have to learn or any of that. People do it for you. And my mentor talked me out of it. He talked me out of it. And I changed the whole way I was doing things. And so that's really how important a mentor can be. And so, and as far as a career as a scientist, well, I mean, I wish I'd have been good enough to be a Major League Baseball player, but that wasn't in the cards. I couldn't, my best pitches couldn't break a pane of glass. So I had to resort to plan B. And, but certainly I don't regret it. I'm still doing it. I mean, this, even though my lab is now closed as of the past year, you can still write what I call opinion pieces. You can go on and be interviewed by insightful young people like you, and maybe get some of your messages across, and maybe some of those people that are hearing them think, oh, let's give this guy some feedback that we don't agree with everything he says. So that's another part of getting a little older in this, that you have to, you're now defending your turf to some extent, but you have to become a good listener now, and realize that you might be wrong on certain things, and that's certainly true. And I've struggled with that, but I'm working on it. And I think that's what we can really teach our mentees, to seek out criticism, to seek out feedback, to seek out the best people you can about your science. And you can't go wrong.
I have a closing question for you. Jerome, can you maybe give your take on the scientific process and the idea of asking hard questions and being wrong?
Yeah. Well, I think I would talk a little bit about that. I think, you know, I think a lot of this is, these bad practices are driven by the competition for grant funding. But we, as Peter Hochachka, a zoologist at UBC, the late Peter Hochachka used to say, don't collect stamps. When you're asking your questions and you're doing your research, don't collect stamps. Be innovative. If the question's tough, go out and seek learning a new method so you can ask it and approach it, or collaborate with somebody else who has it. Collaborative research is not only really crucial though, because it's too complex, it's really fun. I mean, when people have said, you've trained 68 pre and postdoctoral fellows in your lab. I didn't train all of them. Our team did. And the clinicians that I've collaborated with over the years, I learned so much from them, a whole different perspective. The scientific process, yeah, it involves hard work. Okay, big deal. Work ethic's got to be there for sure, but that's only the start. And then you ask a good question, you do the good experiment, you get your finding. And wow, this might be those rare eureka moments that you get in science. But then after you enjoy that for a little bit, think about, I better test this a different way to see if it holds up. Or I better just repeat a couple of those experiments a little more before you rush in to publish it somewhere, or you rush to give it somewhere. I think that's what maturity, I think you learn over time, that you can, and that is so important for, we've been criticized for this, non-reproducibility of findings. And that's a serious, serious criticism. And we've got to be our own educators here and make sure that we really ground our own findings in solid work. If we're wrong, we're wrong. If a better technique comes along or a more insightful approach proves us wrong, fine. But we want to be as solid as we can on the ground. Look at these vaccine developments, okay? I mean, isn't that remarkable when you think about it? That in a period of 9 months, less, these vaccines have been developed. Well, that just didn't, think of all the wonderful basic science. A man who unfortunately died at age 58, a Nobel Prize winner at our university, Howard Timmon, discovered reverse transcription, absolutely essential part of this new development of vaccines. Okay, that happened in the 70s, but to build on that, and when I think back, I got to know him a little bit. I got to evaluate him stuff for some local awards that he won, and looked at his CV and everything. It's kind of nice to see one line on the CV, Nobel Prize, 19. Interesting, fascinating man. And I thought of, looked at all the extra experiments he did to make sure that his hypothesis was not absolutely correct, but reasonable. Okay, and that's what's gone into this ability to. So what worries me are things like, if you look at the other side, are the fact that when we first heard that these vaccines were starting to look pretty good, that they weren't in peer-reviewed publications that were coming up. It was drug companies announcing them at press conferences. That really worries me, because the vested interest is so huge in these people. So it's really good to see it last night that it's gone through at least 3 panels now of objective scientists that have looked at this data. Now, let's be clear. These are very short clinical trials. They're very short. And I wish we'd have had 500 positive cases in the placebo group rather than 80 or 90 or 120. That would make, I think, a lot of us feel a lot better. But it's a hell of a good start. And you think about all the basic science behind that and how careful they're being at this point. That's such an important part of the scientific process. Nice to see, really nice to see. Yeah.
Well, Jerome, I just want to say thank you so much for taking your time out of your day today to talk to me, and hopefully pass on some of those great informations that you have about the respiratory system to all the athletes, coaches, trainers out there who are interested.
John's a real pleasure, and thank you for your hard work in preparing for this. It was enjoyable.
Thank you very much. Have a great day.
You as well. Bye-bye.